equilibrium constant, which we looked at in the previous video. We looked at K and KQ, but this one is going to be specifically of partial pressure. So previously, we've established that regardless of the difference in the concentration of the product and the concentration of the reactants, equilibrium will always be met. So the ratio of this concentration of the product and the concentration of the reactant are always going to be constant. And hopefully you remembered in the previous videos for equilibrium constant and equilibrium constant expressions that this is the definition of what equilibrium constant is. It's the ratio of product concentration and the reactant concentrations. So this would make sense because they're always constant, so this is also what we sometimes refer to as KQ. Okay, KQ would be the permanent equilibrium constant after we've canceled out the pure substances. Okay, and then we've derived this from an actual K value, which was the temporary equilibrium constant. So this here, our K, eventually can become a KEQ at equilibrium, but within that process of calculation, we just simply state it as just K, the temporary equilibrium constant, and that's just the concentration of products on the top and the concentration of reactants on the bottom. Again, see the link in the description below in the previous video where we went over this more in great detail and how we've derived it to make it as KEQ. So we've only done it this way in the previous video, and we've used just the compounds listed, but we didn't actually use molar concentrations put in practice. So that's what we're going to be doing now. The concentration of the gases at equilibrium are this, this, this. Okay, we're going to be putting into practice within this formula over here. Let's first write out what we have. We have carbon dioxide. It is gaseous. We have a reaction reversible, and it decomposes into carbon monoxide and oxygen gas. Now obviously we need to balance it out. Pause the video to give it a try on your own, balance it. You should have gotten maybe 2 here, 2 here, so we got 2 carbons, and we got 4 oxygens. Perfect. Okay, so this is what we need. And now we're just going to use this formula and break it apart and substitute what we need to substitute. Okay, so we have this first product over here, and we have our concentrations up here. We have our carbon monoxide, it's 0.35, and obviously it needs to be squared because of that 2 over there. And oxygens here is 0.15. There is no coefficient over here, so it's just to the 1. And then we have carbon dioxide at the bottom there. We got 1.2, and it has obviously a coefficient of 2, so we're going to do that there. So K is equal to just multiply all these and then divide it by that. What do you end up getting? I end up getting 0.013, so that's your value. And now we're just going to represent this as KEQ, because we've noticed that all of these, this here was gaseous, this here was gaseous, this here was gaseous. None of these are pure substances, and they're all relevant in the constant expression. So instead of a K, we can just put it as KQ permanently. Okay, this was temporary, this is now permanent, and we can just represent it as 0.013. This here is the final answer. At a certain temperature, the value here is 4.2 times 10 to the negative 8. Looks quite small, right? Okay, so in this reversible reaction, what can you infer about the equilibrium concentration of NO, okay, of this one right over here? Well, think about it this way. If our KEQ is this small of a number, And in order to get KEQ, we have to use K here, our temporal equilibrium constant, and K is using these factors over here, the concentration of product on top of the concentration of the reactant. How is it possible to get a value that is so small? Well, let's have a look at an example. Okay, our concentration of the product, let's say it's just, I don't know, like 2, okay, divided by something like, I don't know, 4, 2, 2, 2, 2, 2, 2, 2, 2, or something like a really big number on the bottom. Okay, so what do you end up getting? I end up getting 4.74 times 10 to the negative 9. Okay, so as you can see, quite similar to our times 10 to the negative 8. This is obviously a little bit higher, but they're kind of within the same ballpark. And you notice how this concentration up here 2 is much smaller than this one here, right? This is a much larger. This just kind of puts into perspective how small the product must have been in order for a value to be like this, or for a value to be like that. So what can you infer, okay, about the equilibrium concentration of NO? It means this product here is extremely small. It's very low. It's almost to the point where this does not even react in order to proceed and complete in order to make this product. Because remember in the previous video how if you have a KEQ, okay, and if the KEQ is less than 10 to what value? 10 to the negative 10. Again, see the link in the description below for that video, okay, which is a prerequisite to this video. If you have a KEQ that is less than this, it's almost as if there's no reaction. Okay, and it's almost like that. Okay, this is times 10 to the negative 8, not as bad as times 10 to the negative 10, but as long as you understand the concept that this here is an extremely small number, it's almost to here, which means that there is barely any reaction happening. So within the closed container, there is no actual reaction occurring. Okay, so these here are not forming to make this. On another note, it is preferred for us to apply this KEQ, equilibrium constant, with partial pressure. Since it is easier to measure it this way than using molar concentration, which we just did in the previous example. Okay, however, there is a specific condition. Okay, what is the condition for us to be able to use partial pressure instead of this molar concentration? We have to assume each gas behaves like an ideal gas. Please see the previous video that I've made. Ideal gas rate of reaction. Link is in the description. Now in that video, I explain how we got PV is equal to nRT, this formula over here. This formula, if we were to cancel out some variables here, so if I were to divide this by RT, obviously these would cancel out, right? If I do it on the right side, I need to do it on the left. Then I end up just getting the PV over RT. However, let's try to make this P alone because we're trying to find partial pressure, right? This partial pressure, so it has to be isolated on its own. Right now it is multiplying by V. I don't want that. I need to divide by V because that's the opposite of multiply. Okay, so this is times V. Opposite of that is divide by V. So I've done that. Okay, so if I do it on the left side, I need to do it on the right side as well. Okay, there we go. Obviously this here just changes, so this becomes a multiplication, this becomes a reciprocal of 1 over V, and then PV over RT. These cancels out appropriately, and then we just get P over RT is equal to N over V. Obviously this is our moles, this is our volume, this is our partial pressure, and then this R here is our universal constant, and this here is our temperature in Kelvin. So as you can see, this means that this N over V, what we've looked at in this previous question, right, a couple of minutes ago, this here was our molar concentration. Okay, because this here is our moles, this here is our liters, our volumes. So obviously when they divide together, you get your concentration. And then this here is not molar concentration, but instead it is the partial pressure. Okay, so this here is your partial pressure. I'll just put pp, okay, the partial pressure. And obviously this is all over your universal constant times the temperature. Okay, so this here is your partial pressure of the individual gases, okay, divided by your RT. Now, why is this important? Because if I were to bring this all the way up here, it means that we have a new equilibrium constant, okay? Instead of just K or KQ, now we're going to be representing this all as KP if we start using this one over here as opposed to this one, okay? So if we were to use this one as opposed to this one, okay, this here would now be represented as Kp, also known as the equilibrium constant. Of partial pressure. So, if we were to look at particular products, again, also in the numerator, and a particular reactants in the denominator. So if this was, I don't know, partial pressure, partial pressure, partial pressure, partial pressure, instead of, you know, molar concentration, molar concentration, molar concentration, molar concentration. Well, let's say we put a variable down here, okay, x and then x, okay, so these, okay, variables are going to be representing the partial pressure of each gas. Okay, so this here is your partial pressure, you know, of each gas, okay, but obviously these are dealing with products. Okay, this is the same thing here too. It's the partial pressure of each gas. And then let's say, again, it doesn't really matter, okay, we just use the same variables here, okay, x and then x, okay. This one here would be the partial pressures, okay, of each gas as well, of each gas, okay, but obviously this has to be dealing with the reactant, okay, so maybe I'll just put this here, okay, in brackets reactant, okay, and then this one here would be product, okay, and then this one here is the same thing, okay, this here is the partial pressure of each gas of the reactant, okay, so products on the top, reactants on the bottom. So let's give a try with a few examples. At 1000 Kelvin, the following reaction occurs. And does it look pretty balanced? It looks pretty good to me. And this system reaches equilibrium at 1000 Kelvin. Kp is equal to 7.18. Okay, so I'm just going to write out over here 7.18. Okay, because we know that's always going to be on the side. And then it's going to get into our products over our reactants. Okay, so let's give it a try. So we have in our product over here our SO2. That would be 2.39. Okay, and our SO2, there is no coefficient, so we'll just leave it as such. And then our NO2 would be what, 2.24. No coefficient, so we'll just leave it as such as 1. And then after that we have our SO3. Do we have it? Yep, we have 0.32. And then of course our NO, which we do not have, which we're trying to find in the question, the partial pressure of that, we'll just put NO. Okay, so it should be just pretty simple right now. All you're just going to do is multiply these. Okay, what do you end up getting? You end up getting 5.3536, and then on the bottom here, that just kind of stays the same. You end up just getting 0.32 times your concentration of NO. Now what are we going to do? We're just going to cross multiply here, cross multiply here. So let's give it a shot. So what's 7.18? Multiplied by 0.32 times our concentration of NO, and then this here just kind of stays the same. Give it a try. What would this be? We're getting 2.2976 multiplied by our NO, and this here stays the same. What do you end up getting next? Obviously we have to divide this by 2.2976. Do it on the left side, do it on the right side. So your concentration of NO becomes, and I'm getting 2.33. Now, of course, this has to be an ATM, okay, for our partial pressure. Obviously, if you had an ATM over here, you had an ATM over here, you had an ATM over here, okay, so obviously you would get that squared. This would just be an ATM, okay, so that's square of the ATM minus to the power of 1 ATM here, you're just going to be left over with ATM to the 1 here, or just ATM. Okay, so I just didn't do that within the calculation because it's quite simple. Okay, but if you wanted to do it, you know, properly and then just add in your units throughout the whole expression, that's fine too. Okay, but we obviously know that it has to be ATM here at the end anyway because we're looking at our partial pressure. We have a total pressure of 5.88. Okay, so I'll write this here, 5.88 ATM, and it has a certain composition. Okay, 30% is H2, so for our H2 here, well, it's 30%, right? So you just do, you know, 0.30, okay, multiplied by whatever your total is here. It's 5.88. So what do you end up getting here for your H2? You end up just getting 1.76. Okay, and then that's obviously an ATM. What else do we have? Well, we have the CO2 over here. So what would that be? That's 28%. So you just do 0.28 times our 5.88. What do you end up getting for that one? Then we're getting 1.65. Okay, also an ATM. And the rest is going to be, the rest is going to be for HCl. Which is going to be the remainder. Okay, so we've done 30% here, 28% here. What does that give you? That would obviously be 58%. Okay, so then the leftover of that, so you just do 100 minus 58. What would that give you? It gives you 42. Okay, so we'll just do 0.42 times our 5.88. What do you end up getting for that? You get 2.47. 2.47 ATM. Okay, so now that we have our partial pressures, we just have to determine the Kp. So let's bring this up here. Okay, so the Kp is going to be our products. Okay, obviously we have this and this, and it seems to be all balanced out now anyway. So H2 and Cl2 we're going to be putting beside each other. So H2 is going to be 1.76, and what else do we have? We have Cl2, 1.65, and then our denominator here is 2.47. And this one has a 2, so we got to put that up there. What do you end up getting for your answer? I end up getting 0.4759. And of course, this would make sense in terms of the units. Again, we know that there's not supposed to be any unit anyway, okay, because we're obviously looking for Kp, okay, we're not looking for molar concentration or partial pressure, okay, but let's say if you wanted to backtrack and you wanted to just look at them unit by unit for them to cancel out appropriately. Well, this is ATM, this is ATM, this is going to be squared. Okay, this ATM is already squared. Okay, so you just, you know, cancel them out. So obviously you have no unit there for ATM. Okay, so we're just going to be left with this. So this is correct. All right, these are the two green questions of the day. That's the first question. This here is the second question. Give this a try on your own. Pause the video and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.